Hi guys, welcome to lesson 10-1. This lesson is going to be an introduction to vectors. When we describe physical phenomena such as wind or a current in a river, we look at the direction of the force and its strength. These properties can be described by using vectors. Vectors are used to describe a wide variety of real-world forms such as wind, velocity, and force. In this lesson, you will be introduced to the concept of a vector. We'll go ahead and get started here. So first of all, if we're going to define what is a vector is a quantity that usually has two characteristics. Those two characteristics we have are magnitude, which we can describe as like a size or a length, and then it has what we were just talking about above, direction. And we will break those down and talk about those a little bit more specifically here as we go through this lesson. Okay, now there's a couple ways that you will see vectors denoted here when you're writing them. Before I do that here, I'm going to show you examples. Here are examples of two vectors on the right side. You'll see there we have vector v, and then we have vector ab. Okay, so sometimes when it's named, you'll see that like that vector v. Sometimes you'll see it'll be just a bolded letter. That's how you know that it's a vector. It's a bolded letter. And I do my best there to kind of bold that there, right? This is bold. So that would be vector v. Okay. Now, sometimes it's named with 2 points. And when it's named with 2 points, usually you have like an initial point, and then you have a terminal point, right? An initial point where it starts, and then a terminal point where it ends. And you can tell the direction it's going because it looks like a ray like you would have seen in geometry. So that second vector that we see there would be vector AB, and sometimes they're written like this. You see you have AB, and then you have like a half of a ray on top of it. This would be considered vector AB. And it can be written with this as a single letter with the ray symbol above it as well, just like we did with the AB. It can be done with one like that as well. So, actually, I'm going to even write that down so we're not confused by that, right? So that vector V could also be written like that as well. All right, so something you need to know, because they have magnitude and a direction and things here, right? We're going to be describing how these look. And one way we describe them is using what we call component form. Component form looks something like an ordered pair. Okay, you've got two numbers that'll be separated by a comma, and instead of having like parentheses or brackets, they're kind of like pointed parentheses. That's how I would describe them. Okay, the first value is going to describe the horizontal component. And I'll describe what that is here in just a second. Okay, B is going to be our vertical component. So basically they're going to describe which direction it's going. If we look at vector V, okay, obviously it starts here at the top. Okay, if we were going to describe this by its horizontal component there, right, notice this one does not go left or right. So in writing its component form, we would have a 0 for the horizontal component. And then you notice it goes down 1, 2, 3, 4, right? It goes down 4 units. So our vertical component would be -4. So just like you're used to with numbers, right? If you're going left, that would be negative. If you're going right, that would be positive. If you're going down, it would be negative. If it's going up, it would be positive. So let's look at our vector AB, right? If we start here at that initial point, it's going to go to the right 1, 2, 3, 4, right? So it's going to the right 4 units. And it's also traveling up 4 units, right? So you can almost think about it like it's slope of a line, if you remember that from Algebra 1. But what we've got here, right, since it's going to the right 4 units, we know it's a +4. and it's going up 4 units, so that is also a positive 4. All right, let's move on. It asks us to draw a vector that represents a 15 mile per hour wind blowing from the north. So just thinking about our compass rose, right? We've got north always being at the top, right? And then we've got east, south, and west. Hopefully we know that. But if it's blowing from the north, that means it would be blowing towards the south. So if we were just trying to illustrate this vector, it would be a ray that's pointing downward towards the south. And then we would label it with a 15 there because it's 15 miles per hour. Okay, so let's talk a little bit about direction and magnitude. So direction basically is going to be, we're going to treat it like it's an angle, and we're going to be measuring it from the standard position. So let's just record that down here. So usually we'll use like something like theta, but we have an angle, measurements from the standard position. So we have an angle measurement from the standard position. And if you don't remember what I'm talking about, standard position, right, that's where our positive x-axis is 0. Right, just like you would measure if you're using the unit circle. Right, if we took a here, right, and we were thinking about, I have this vector. Let's say this vector had an initial point here and went out like this. Okay, if we were going to measure that angle, right, we'd start here at 0 degrees, and we would measure all the way out to here. We would say that that vector, if I was estimating, right, would be about 135 degrees, right, because it opens up that way. Or, right, we could take it, we could say, hey, we could go in that negative direction, go around here like this, in which case we'd have, what, a negative 225 degrees? Okay, but that's what it's talking about when we're saying the direction. So the direction is the angle measurement from the standard position. Now magnitude, okay, magnitude is just simply the length of the vector. Okay, sometimes it's easy to measure them, sometimes it's a little bit more challenging. Okay, now the notation, what you'll see, like for vector v, we still have there, right? When it's asking you, hey, what is the length of v, or what is the magnitude of v, you'll see a v, and then it almost looks like it's got like a double absolute value on it, right? So this is basically asking, what is the magnitude of v? Okay, so you could also see it as, you know, for vector AB, you'd see that in there, you know, the same kind of thing. That's like saying, what is the length of AB? Now, how do we find the magnitudes? Well, it just depends. Let's look at the first one. Let's look at V right here. So when it's just a vertical vector here, right? It doesn't have any horizontal. It doesn't have any horizontal influence on it, right? It's not going left or right. It's just going up or down. That makes it easy because we can just count. Ready? 1, 2, 3, 4. Right? It's going down 4 units. Right? So our magnitude for vector v would be 4. It's just that distance. Now with AB, it might be a little different, right? Because we can't just count them as we're going along our vector AB. So what we're going to do is we're going to take into consideration our horizontal component, right? Which our horizontal component, it went this way 4 units. And now it's going to travel up 4 units. So in order to figure out the distance of that whole thing, I'm sure you probably already can recognize that we'll just go ahead and use our Pythagorean theorem. Right? We'll take our 4 squared plus our 4 squared should equal like our c squared, right? If we were going to do it like Pythagorean theorem. Okay, but we know then we're going to be taking the square root of this, right? So to get our magnitude of vector AB, we're just going to use that expression. So we'll say what? Square root of 16 plus 16, or square root of 32, which would then be 4 radical 2. Okay, so that is our magnitude for vector AB. So if you wanted to even just like write down like a little formula or something, we could do that. Let's just say like the magnitude should always equal the square root of that horizontal component squared plus that vertical component squared, right? That's like our a squared plus b squared equals c squared, or the distance formula. All right, so let's jump down here, and I guess it says find the magnitude and direction. We already found the magnitudes, right? So the magnitude for vector v was 4. For AB, it was 4 radical 2. And what we'll do now, though, is we'll find our direction. So with our direction, if we just kind of visualize that we're starting at the origin with that initial point, so like vector v went down like this, right? So if we were just going to measure around, right, we'd start at 0. There's 90, 180, 270. We could tell that this is going to go 270 degrees. So for v, we've got 270. Or you could say it went backwards this way and went negative 90 degrees. So either of those would be correct. And then if we were looking at our vector AB, right, we're looking at its direction. Okay, so we'll kind of give it a little sketch. And that one goes up to the right like this. And we already know that it's going to the right 4 and then up 4. Right, so as we think about that, we've got a right triangle and it's isosceles. So we know that this is going to be 45 degrees. Right, so sometimes they're pretty easy and you can just see what it's going to be, right? Our angle measure there would be 45 degrees. There's not really a sense in going backwards to come up with a negative on that one, right? So we'll just say it's 45 degrees. If you have questions, please make sure you mark them down. Let me know. All right, the next few slides are just going to have us work on finding some information about some vectors. So we'll start with the fourth slide, which says write the component form for all vectors to the left. So you'll see we have about 7 vectors, and we're just going to write them all in component form. So starting out here with B, right, as we look at it there, we're just going to write it in this form. So it looks like it starts here and it goes to the right 1, 2, 3, 4 units. So we know the horizontal component is 4. It's not going up or down, so we'll call that 0. The next one we'll look at is Q. It's going down to the right. So as we look at the horizontal component, looks like it's going to the right 2. And then it's going to go down 1, 2, 3. So we're going to have a negative 3 for the vertical component. So if you want to go ahead, you can either pause the video or just fast forward through, do these, and check to see if you get them all correct. If you need help on any of them, continue watching this part. So for D, looks like we've got a horizontal component of 0, and then it goes down 1, 2, 3, 4, 5, 6, so 0, negative 6. For A, it went to the right 2, and then it went down 3. For V, we've got to the right 1, 2, 3, 4, 5, 6, 7, and up 2. So right 7 and up 2, so we've got 7, 2. W, right, looks like it's going back to the left 2, back to the left 2, and then up 3. So that one's going to be negative 2, positive 3. Which you see is different than what we have for A and Q. And then we've got F, which doesn't move left or right, so we've got a 0 for the horizontal component, and then it goes up 6. So hopefully you got all those right. Let's move on to part B. It says, what do you notice about the component form for vectors A and Q? As we look at that there, our component form for A is 2, -3. For Q, it's also 2, -3. And you can tell here that those are going the same direction and are the same length. So we could say that they're the same. I believe that was 2, -3. Okay, and then letter C asks, vectors that have the same magnitude and direction, like A and Q, are called equivalent vectors. Okay, so when they have the exact same magnitude and direction, we refer to them as equivalent vectors. Letter D asks us to draw a new vector M that is equivalent to V. So if V has a component form of 7, 2, we're going to go ahead here and have to draw in one that's equivalent to that. So I'm going to draw it down here. I'm going to start it here. I know I'm going to go to the right 1, 2, 3, 4, 5, 6, 7, and then up 1, 2, right? So it starts here. Here's the actual vector coming in. And we know this is 7, this was 2, so this was our vector M. So you don't actually have to draw the whole triangle, I'm just trying to emphasize to you how to do it. So vector M is highlighted there, so it's just the ray. Alright, so we got that one, and then it asks us to find two vectors that have the same magnitude but go in opposite directions. So our vectors have the same magnitude but go in opposite directions. We could say here, well, if we look at W and A, right, they would have the same magnitude, they're the same length, but they're going in opposite directions. And then we could also look at D, right, and F. They have the same magnitudes, but are going in opposite directions as well. So we can throw in there A and W, which we know also could have been Q and W as well, if you wanted to put that. And then our second pair was D and F. And then it asks us to find the direction of vector V. So when we do that, let's think about what it looks like. We've got that vector starts and goes to the right 7 units and up 2, so something like this. So if we're going to take it and we're going to like kind of sketch it in, think about it being like a right triangle, right? We went to the right 7 and we went up 2. Now if we're trying to find the direction, remember the direction is that angle measured from the standard position. We're trying to figure out what this angle is. So since we have a right triangle, that should make it a little bit easier for us, because we take that right triangle and we think about our trig ratios. It should be the tangent of theta should equal the opposite over the adjacent, or 2 over 7. So to find our angle measure, we will just do the inverse tangent of 2/7. And you may want to grab your calculator out to do that. Make sure you double check that it is in degree mode. Mine's in degree mode here. Alright, and so I'm going to do the inverse tangent of, we said 2 over 7. And you'll see we get about 15.945 degrees. So theta is 15.945 degrees. Let me double check that I put the right number down. Yes, I did. If you have questions, please make sure you mark that down. Let's move on. Okay, now this slide says when two actions are performed sequentially, one right after the other, we can combine them into a single action, which will give us the same result. Okay, so let's look here at doing that. Okay, so we're given an initial point right here, and they ask us to first go down 3 steps. So if I went down 3 steps, I'll do that in red. Right, I'm going down 1, 2, 3. I went down. This was step number 1. And then it asks us to then go to the right 4 steps. So that'd be 1, 2, 3, 4, right? We went to the right 4 steps. This was that second step. Okay, so we could either choose to do that, go down 3 and then to the right 4, or it might be considered more efficient to take it and start at that initial point and go this direction down to right there. Okay, so when we take two vectors and we add them together like that, that vertical vector and that horizontal vector, and we have that shortcut that's left over like this, right? If we wanted to use that shortcut, what we refer to this as is the resultant vector. Okay, that is our resultant vector. So instead of going down 3 and then to the right 4, it would be more efficient for us to just go straight from the initial point up here to the ending point down there. Now they want us to find the direction and the magnitude of this resultant vector. Okay, so we can take it and do that. So let's think about the component form of this first. Right, so if we started at that top point and went down 3, right, we've got -3 because we're going down. I'm sorry, we're not going down first, right? We want to write it horizontal, then vertical. So you're thinking about, like, we could say, oh, we're going to the right this way and then down, right? We always write our horizontal component first, which means we're going to the right 4 units, and then we're going down 3 units, so -3 there. Okay, so just thinking about that's our component form. Okay, so finding the direction. Okay, we could do that. Let's take it here. And if we were to draw this one in, this one starts and goes down this way. So we know that we've gone 4 to the right and 3 down. Now you can do this with a negative there, or you can do it with positives, okay, to help us find out what this angle is. Okay, so when I do that, I could say, hey, my tangent of theta should equal my opposite over adjacent, which would be 3/4. So inverse tangent of 3/4. I remember I wrote it as positives, which we know that this is really a negative down here, right? We're going down 3. But if you do it with the positive, it's going to give you the reference angle, which is all stuff you already know. But let's go ahead and calculate that. So we'll say inverse tangent of 3/4. You'll see it's 36.870. Okay, but we know that that's a first quadrant angle. So if we're thinking about going down this way, right, that would be a -37.870, or we could think about going all the way around the circle this direction, right? We could do that by saying 360 minus 37.870. And when we calculate that, we'll just subtract that there. All right, looks like 323.130 degrees. So either of those answers would be correct for the direction. As for the magnitude, this one's pretty easy for the magnitude, because if we look at the triangle's sides here, right, we've got a 4 for a leg, we've got a -3 for the leg, right? And if we do our magnitude, right, if we did 4 squared plus -3 squared and then took the square root, we're going to end up with the square root of 25, which is, oops, not the square root of 5, it's just 5. Right, it's just a 3, 4, 5 right triangle. Okay, so the magnitude is 5, and then our direction is either 323.130 or -37.870 degrees. Moving on. So adding vectors geometrically. It says, given the 3 vectors shown below, find the resultant vector for r plus m. Okay, so we've got m, p, and r, and they want us to take this r and they want us to add m to it. So when we're adding m to it, it's like one of those sequences that we did here a slide or so ago, right? So after I do r first, my sequence would be finished by m. So we're adding r plus the m. So when we do that, let's start at the end and we'll go down 2 units, just like that, right? So our resultant vector is going to be the one in blue. This is our resultant vector. This is r plus m. Okay, so if we took it and we kind of compared these, our initial vector that we had there, that r, whoops, those aren't parentheses, we need the little pointy ones there, right? For our horizontal component was 7, our vertical component was 2 for r. For m, we had a 0 for our horizontal component, and then it looks like -2. And then for r plus m, right, if we look at that one, it looks like it's gone to the right 7 units, but it has not gone up or down. That'd be like 7, 0. So if we write those out, let's do that real quick. Let's just write that on the side over here. We have r, which was 7, 2, vector r. And we had vector m, which was 0, -2. And then we ended up with r plus m, and that is going to be 7, 0. Okay, now they ask us to do this again. They're going to say, hey, let's do r plus p this time. So r, we already know is 7, 2, so we'll draw that in here. We've got 1, 2, 3, 4, 5, 6, 7. Actually, let me move it back 1. So 1. Sorry, I'm just out of room trying to make sure everything fits. So I think that should hopefully work right there. Right, so there's our r. We know that p, shoot, it's not going to fit on there, is it? Come on, Mr. Boyd. Let's just move it back 1. There we go. Okay, so we'll add our p to it, right, which our p looks like it's got a horizontal component of 3 and a vertical component of -3, right, because we're going to the right 3, and then we're going down 3. Okay, so we'll go to the right 3 and down 3 from the very end of r. Which looks like it's going to take us right over here. So there's our p. And that means that our resultant vector would be this one. It goes from here to there. So this is r plus p, or we'll call it b, is what they said. So, interesting thing here is when we look at these, right, we had vector r was 7, 2. We had vector p, which was 3, -3. And then we had our vector b, we'll just call it now, right? And that one, what's its horizontal component form? Well, it looks like it goes to the right 7, and then we go 3 more, so we have 10. And then it goes down 3 units. Let's see. Or 1 unit on that one, right? So -1. All right, because we went to the right 7, and then, 10, and then down 1. Sorry, I'm rushing, trying to get this done. So, you can see how we're adding them geometrically by just continuing on to the end of each vector with our new vectors. Okay, now we can also see, though, that algebraically, if I start out with these two, and we're adding these together, right? If I add my horizontal components, it'll get me my new horizontal component for the resultant vector. And if I add my vertical components, it'll get me the resultant vector's vertical component as well. Same thing down here, right? 3 plus 7 gives us 10, and 2 plus -3 gives us -1. So you can add them algebraically or geometrically by showing it on a graph. And then D is just asking us to put that all together. We'll just write that out as a rule so that you can see it and refer back to it in your notes if you need to. So let me look at that there, right? If I had, in this case, let's say vector U, and its horizontal component was, like, let's say U1, and then its vertical component was U2. And then if we had vector V, we'd say, hey, that's going to be V sub 1 and V sub 2, right? In order for us to get the components for U plus V, we would take this and we would say U sub 1 plus V sub 1, comma, U sub 2 plus V sub 2. And there you go. All right, let's go into the last slide here. This is just a little bit of a kind of a challenge problem for you. It says, in the diagram below, vector V is added to vector U, which is not shown, to get the resultant vector W. It says, what is the component form of U? So it's starting with V, and it goes this way. Now vector U, right, would have to be coming out from here in some direction, right? And wherever it goes out from, you don't have to write that on your paper there, but it comes out from there. Wherever it goes, whatever direction it goes in, okay? When we start at this point, okay, it's got to end, at the end of this here, that would give us our resultant vector. So I realize I didn't explain that very clearly, so let me just start again. So we're taking vector V, I'm going to do it algebraically and then we'll show you geometrically. So vector V, our horizontal component is 2, and then vertical component is -3. We're adding to that something, right? Something for vector U, and our resultant vector is vector W. Okay, now vector W has a horizontal component of -3, -1, right? And if we were looking at it geometrically, W would go something like this, right? So, because whatever we add to V should get us to this point here where our W ends. So we're going to add this plus something, right? Well, we're going to have to add it to something that gets us all the way over here. That would be our vector U. So when you look at it that way, vector U should have 1, 2, 3, 4, 5, and -5 for its horizontal component. And then it looks like it's going up 2, so we'll have 2 in there. And if you check it here, 2 plus -5 is -3. -3 plus 2 is -1. So it all matches and works out. All right, if you have questions, please